Hello everyone, I'm Salimzadeh. I'm here on behalf of my colleagues Neel P. Bhatt and Dr. Ehsan Hashemi, presenting to you our work on augmented visual localization using a monocular camera for autonomous mobile robots. When we talk about automation in navigation, every robot has to ask itself two questions. First, where am I? And then based on the information that I gather about my own location, what should I do? Here we try to answer the first question. Localization with onboard sensors has been well investigated in the Islam community. But the problem with onboard sensors that move alongside the mobile robot, is gradual drift in localization estimations. One way to tackle this problem is by using fixed cameras to localize the robot and communicate the results with the actual mobile robot. This has applications ranging from warehouse or service robotics to surveillance. The picture that you see is from one of the JD.com's fully automated warehouses that are using the same technique. The test setup that we have for this research has one fixed mono camera with a fisheye lens observing a jackal mobile robot. On top of that, we also have a motion capture camera system, which we denote as V. But we have to note that this motion capture camera system is pretty precise and is only used for evaluation purposes. So only to generate the ground truthing for our algorithm. Because we are using the fisheye lens to increase the field of view, the main disadvantage with this method, with this choice, is the heavily distorted frames. So first, the step for working with this kind of distorted data is to undistort the frames, which we do using the fisheye camera model. The second step is to actually locate the robot with an object detection algorithm, namely YOLO, to see where the robot is in the 2D frame and then try to recover the 3D location of this robot. But moving from a 2D image plane to the 3D requires one more dimension, which in our case is our depth. So to recover or reconstruct the depth map of the field of view of the camera or the frames, we are using a machine learning algorithm called MyDAS that gives us the estimate of the depth map of each of our frames. This is only one example of one of our undistorted frames and the corresponding depth map. The advantage of using this method over stereo vision or using depth sensors is the cost of operation. So we only have one low-cost camera and no other auxiliary sensor to deal with. After this, we do have the depth map, we do have the location in 2D, so we can actually project whatever pixels are inside the 2D bounding box coming from the object detection to the 3D world and come up with a point cloud around the robot, or the points of interest as we call it. I have to note that the point cloud of the whole environment shown in this picture is only drawn here for visualization purposes, and we're not actually projecting every point in our frames to the 3D world because it's just not computationally efficient. So we are only projecting the frames that lie inside the bounding box of the object detection algorithm. The problem with object detectors is that it gives you a bounding box and you don't actually know the exact pixels that are on your object, which is in our case the mobile robot. So there could be some points that lie on the ground. There could be some outliers in that point cloud. So we have to do some filtration steps in order to get rid of these outliers. The ground points are the easy part. So because of the prior knowledge that we have of our environment, namely ground is flat, and also the location and pose of the camera with respect to the ground, we can just simply threshold the ground points and get rid of those points that actually lie on the ground. And the second step is to get rid of other outliers that are in low density neighborhood areas of the point cloud. So simply put, Any point that is far away from its neighbors is perhaps an outlier, and we can reject them by measuring the density of this point cloud. So after the filtration step, we are left with this red region that we are showing in this picture, which corresponds to the actual mobile robot. By calculating the centroid of this red point cloud, we can come up with only one point, which is going to be the location measurement for our point cloud at that time step. The problem with the visual sensor that we have is that it is uncertain, as is any other sensor in the world. So to deal with this uncertainty of the measurements, we are trying to fuse this the sole source of information with another information, prior information as I should call it, about the robot to try to come up with a way to decrease the uncertainty or the errors. And the way we chose to do this is to come up with a motion model for the robot, design a motion model, and fuse these two information together in a Kalman filter. So the motion model that we are using here has a simple assumption. Namely, between each timestamp, or 100 milliseconds, the robot only has a single acceleration in X and Y directions on the ground. And so the motion model of the robot is going to be a constant acceleration motion model. The states of this motion model are position and velocity of the robot in X and Y direction, and the inputs are accelerations in both X and Y direction. To estimate the inputs to the motion model, we're not just relying on double derivation of the location history because it produces a lot of noise into the acceleration data. So we have designed a deep neural network to be able to estimate the acceleration of the robot with the noisy inputs from the camera. So this deep neural network that we have designed consists of 15 fully connected layers. Each of the neurons in these layers have tanh activation functions, and we also use batch normalization in training to speed up the training process and also increase the network accuracy. The input to this network is a moving horizon of location measurements coming from the mono camera with the fisheye lens, and the output is the estimated acceleration in each of the X and Y directions. The ground truth thing that I mentioned in the test setup coming from the motion capture camera system is used here. So the main objective of this deep neural network is to be able to estimate the actual acceleration that has been computed based on the precise location measurements coming from the motion capture camera system. To fuse these two sources of information, we are using a Kalman filter with an adaptive covariance tuning. So let me tell you about this adaptive covariance tuning. The idea behind it is that visual informations degrade with depth. So what I mean by this is that when an object is far away from a camera, there are not a lot of pixels on that object. So we don't have a lot of information from that object. Because of this, we can tune the covariances of the process and the measurement to be able to rely more or less on any one of them. Namely, when the mobile robot is closer to the camera, we rely more on the measurements that are coming from the visual node. And when the robot gets far away from the camera, we know that the camera is going to produce some noisy measurements, and it's going to be more uncertain. So because of that, we try to rely more on the motion model of the mobile robot rather than the visual measurements. So it's just a simple switching scheme going on around here. The only thing that we have done here is we've used the tanh function to kind of smooth out this transition between relying on the process or relying on the measurements. So here we're trying to showcase some of the capabilities of the proposed algorithm. So right now in this picture, you can see that half of the robot is occluded with the presence of the human in the environment. But even though half of the robot is not visible from the view of the camera, the localization algorithm could at least pick some of the points that are on the camera and denote that location and get the location measurement for them for that instance or timestamp. Here is the result of the first scenario that we tested for this algorithm. As we can see, the robot had a pretty complex trajectory in this test scenario. But even though the trajectory was complex, it could be estimated using the proposed algorithm. The second testing scenario, we've tried to challenge our algorithm with a failure situation for the visual node. So what happens if the cameras actually fail to localize our robot? So here, the mobile robot is moved out of the frame or out of the field of view of the camera on purpose, and again put into the field of view after some seconds to see what happens in this case. So as you can see, the algorithm is able to reinitialize the state estimation process and carry on with the trajectory estimation. In the third results that I'm showing you here, we have sporadic occlusions with the human agents that we have in the environment. So even if you have an office or a warehouse that robots and humans are working symbiotically alongside each other, it doesn't matter if you have occlusions in short amount of times, but often. In that case, our algorithm is also robust to these kind of sporadic occlusions. To sum up, we have presented an infrastructure-aided mobile robot localization algorithm using only a single fisheye monocular camera as the source of information. The future research avenues that are ahead of us are first improving the computational efficiency for achieving sampling times that are less than 20 milliseconds. Also augmenting the motion model of the robot with lateral dynamics using side slip angles for scenarios that the robot is moving on a harsh surface outdoors, and also estimating the heading angle of the robot for more detailed localization. Thank you for your attention and time, and we would also like to thank our sponsor, NZERC, and also the University of Waterloo's RoboHub, which helped us a lot to get our own data set for this research.